Welcome to Pre-Calculus, Section 5.2 on inverse functions. First, let's look at this definition. Suppose f and g are two functions and that the composition of g and f of g both equal x. Now, we learned how to do g of f of x and f of g of x in our last section on composition. So we find these two things algebraically, we simplify them, and if they're both equal to x, then we can say that the functions f and g are said to be inverses of each other. Or said another way, f and g are invertible. So this is how you determine algebraically whether f and g are inverses of each other. Next, we need to understand what is meant by saying a function is one-to-one. So a function is one-to-one if the function f matches different inputs to different outputs. Or we could say that f is one-to-one if and only if, whenever the y's are equal, then the x's have to be equal. And we'll do some of this f of c equals f of d, then c equal d type of proof a little later. Now, the other way is we can detect one-to-one functions using the horizontal line test. A function f is one-to-one if and only if no horizontal line intersects the graph in more than one place. So let's look at three cases to understand the idea that a function is one-to-one if f matches different inputs to different outputs. And the idea that if the y's are equal, then the x's have to be equal to say that a function is one-to-one. And we'll tie that into the idea of that function would have to pass the horizontal line test in order to be one-to-one. So let's say I have this set of xy pairs here, and I've graphed them over to here. So what you can see is that you've got repeat values in the y. So if you try to see whether this thing passes the horizontal line test, it's going to fail right here. So it fails this idea here because f of 1 and f of 2 are both the same number. Okay, that fails this case here. And also you can see it illustrated in the diagram where a horizontal line would go through two different dots. All right, let's look at two more cases. All right, so let's look at another case. Here's the case where you've got repeats in the x. So in this graph over here, I've got these three dots that represent these points. Okay, so it's going to pass the horizontal line test just fine, but it's not going to pass the vertical line test. Okay, so if it doesn't pass the vertical line test, it fails on the first idea that it's not a function in the first place. So if it's not a function in the first place, we wouldn't even look to find out whether it had an inverse. And here's the last case. Here you can see that you don't have any repeats in x, you don't have any repeats in y. So you pass the vertical line test, meaning it is a function, and you pass the horizontal line test, meaning it's one-to-one. So we can conclude that it is a function, that the function is one-to-one, and that the function is invertible, meaning it has an inverse. The next idea is the idea here of uniqueness of inverse functions. So what that means is if we know that f is an invertible function, there's exactly one inverse function for f, denoted by f inverse. So the symbol f with a little -1 in this position here, in the power position, is read f inverse. There's a note that I'm writing down here that says f inverse is not the same as putting that -1 on the outside of f of x. F inverse is right beside the f here, and it's in between the f and the parentheses. Okay, this is a symbol in and of itself. Now, if you put the -1 on the outside, what that's telling you is that you're putting f of x into the denominator, and that's an entirely different meaning. Now let's look at this graph that I've drawn here. Now I have the function here, f of x is equal to x squared, and in order for that to be a one-to-one function, I can only have this restricted domain over here, or I could have this restricted domain over here. But if I graphed the entire parabola, it would not pass the horizontal line test. So sometimes you'll find when you're studying inverse functions is that you have to only take a piece of the graph of f and say it's invertible only over a portion of its original domain. Okay, so if I look at this piece of the quadratic function from 0 to positive infinity, it has an inverse, and its graph is this purple line here. So I would denote f inverse as the square root of x. Now I haven't shown you how to do that yet. You may remember from Algebra 2, but at this point I'm just showing you what is meant by the uniqueness of the graph. So if, and I'm telling you these two are inverses, you should be able to fold up on this line here, y is equal to x, and this graph will then lie on top of this graph. Okay, and that means they would be reflections of one another over this line. Okay, and you can kind of imagine that that's going to happen if you fold on this line. This purple graph is going to lie on top of this brown graph. So that's the idea here, that the graph of f inverse is the reflection of the graph of f of x across the line y is equal to x. So in essence, y and x switch places. So what we've learned so far, there are several ways that we can state the same thing. Suppose f is a function, then these three statements are equivalent statements. So the first one, f is invertible. Second one, f is one-to-one. And the third one, the graph of f passes the horizontal line test. In all three cases, we're saying f has an inverse. So let's practice this one time. So this says, determine if the table represents a one-to-one function. So remember, when we're looking for a one-to-one function, we want to make sure we don't have any repeat values. So when I say no repeat values, what I'm saying is no repeats in the x column, no repeats in the y column. So if I look at these three tables here, let's look for repeats. Okay, so these are unique, and these are unique. This one looks like it's one-to-one. Here I've got 2 7s in the x column, so those are repeats, though this one is not one-to-one. And here I've got repeats in the y column, so this table here, this is not one-to-one. So right here, this is the only one that's one-to-one. This is the only one that is going to be invertible. So let's look at this question here and try to understand the f inverse notation a little better. So we know this notation here. This just says find f of 6. That means when x is 6, what is f of 6? So we look in the table here. When x is 6, f of 6 is 0. Now the next line says, if f of x is equal to 1, then what is x? So we're given the output 1, which is your y, and we're trying to find the x that gives us that 1. So we're going to look in the output column for 1. There it is. The input value was 8. So let's make a little arrow diagram. So when x is 6, the output is 0. So I'm going to say 6 maps to 0. And then when x is 8, y is 1. So I'm going to say 8 maps to 1. And that's going to help me down here when I start dealing with f inverse. So when you invert a function, what that means is that if x is mapped to y for f, then y is mapped to x for f inverse. They switch places. So I'm going to put an arrow on in a different color, blue, for the inverse. And that tells me which way I'm going to map when I figure out f inverse. So now let's look down here. So now I'm dealing with the function f inverse. And so I'm saying the input now is 0. So remember, I'm going this way now. So if the input is 0, then the output is 6. So f inverse of 0 has to be 6. 0 is mapped to 6. And then if I look down here at the last question, it says f inverse of x is equal to 8. So I'm given the output, and I want to find out the input. So I'm looking at my blue arrows. Here I can see input is 1, output is 8. Okay, so the input that gives me an 8 is this 1 here. So it's 1. So here's another similar example. We're going to use the graph of f of x to pick off our values to figure out our responses here. So the first one says f of 0 is equal to some value. So that means when x is 0, what is y? So if I look at the graph, when x is 0, that means y is 3. So that means 0 maps to 3. And then for the second one, it says f of x is equal to 0, so that's your output value. 0 is your y. So let's just write a y here. So when your y is 0, that means what would your input value be? What would x be? So when y is 0, along this line, x is 4. So let's just write a 4 here. So that means 4 maps to 0. So now we're going to talk about the inverse function questions. So let's draw our arrows going back in the other direction to represent which way we would map for f inverse. Okay, so now we can answer the question, f inverse of 0. So if 0 is the input, what is the output if we're going in the brown direction? So that means I'm going to look here. So if 0 is the input, 4 is the output. And then the last one says f inverse of x is equal to 0. So we don't know the input value to the inverse function, but we do know the output value is 0. So if I look at my brown arrows over here, my inverse function goes this way, input to output. So if my output is 0, my input must have been 3. Okay, so make your little arrow diagrams here so you can switch directions when you start talking about f inverse. All right, now let's do some algebra. So what we're asked to do here is determine if the following functions are one-to-one in two different ways. First, analytically by using this definition here that says a function is one-to-one if and only if, when the y's are equal, then the x's are equal. And then we'll look at it on a graph and show that they're either one-to-one or not using the horizontal line test. So let's take a look at number 1 here. So we've got f of x is equal to 1 minus 2x over 5. So we want to use this definition here. So we're going to set up f of c and set it equal to f of d, and then back out by simplifying whether we do get c is equal to d. So f of c would be 1 minus 2c over 5. And we're setting that equal to f of d. F of d would be 1 minus 2d over 5. And now we're going to simplify, and we'll find out whether c is equal to d or not. So if I simplify this, I've got a 5 on either side. Cross those out. So I've got 1 minus 2c equals 1 minus 2d. I've got a 1 on either side. Cross those out. And then I've got a negative 2 that I can divide through here, and my last line will say c is equal to d. Okay, so we've started out with f of c being equal to f of d, and we've simplified to the point where c is equal to d. If that's the case, then we're going to say this function here is 1 to 1. Let me just simplify that, 1 to 1. All right, now on a graph, this function is, all right, so I went back and actually wrote 1 to 1, but on a graph, this function is going to look like a line, because if I say y is equal to, if I put the 5 under the 1 and the 5 under the negative 2x, I can see that this is a line with a slope of negative 2/5 x and a y-intercept of 1/5. So it's going to be a downward sloping line, something like that. Well, any line like that with a slope on it like this, in this fashion, you could see is going to pass the horizontal line test. That also indicates 1 to 1. So let's look at number 2. So first we'll set up f of c equals f of d. So that's 2c, 1 minus c, 2d, 1 minus d. So I can cross out those 2's. So I've got cross multiplying c times 1 minus d is equal to d times 1 minus c. So distributing, I've got c minus cd is equal to d minus cd again, because that's the same thing as dc. All right, so I can cross these off, same on both sides. So my last line will say c is equal to d. Okay, so starting out with f of c equals f of d, we've shown that c equals d, which that this function is also 1 to 1 by that method. Now we want to show graphically that it passes a horizontal line test. So I'm rewriting it so I can find out what my horizontal and vertical asymptotes are. So remember, the horizontal asymptotes, you take the highest order term. So my horizontal asymptote is going to be y is equal to 2 over negative 1, which is negative 2. Then I look at my denominator, and I'm going to say my vertical asymptote is x is equal to 1. So then if I graph this function, I'm going to get a branch down here and a branch up here, and you could verify that. And if I try to pass a vertical line through it, I'm going to be able to verify that I won't pass more than one place on the graph. I won't pass through more than one point, which means it passes the horizontal line test, which means the function is 1 to 1. So we've shown it both ways. Now let's look at number 3. So I've got to set up f of c is equal to f of d, so that's c squared minus 2c plus 4 equals d squared minus 2d plus 4. So I have a 4 on either side. So I have, let's see, c squared. Let's bring all the squared terms to the left and all the non-squared terms to the right. And I can see this isn't looking too good for simplifying down to d is equal to c, but let's just see if we can get a little further. So let's see, this will factor, difference of two perfect squares. I can factor a 2 out of the other side here, so I've got 2 times c minus d. All right, so I can cancel out c minus d. But then I have c plus d has got to add up to 2, or I could say c is got to equal to 2 minus d. Well, that doesn't say c is equal to d, so this function can't be 1 to 1. So we'll say this one is no. This one is not a 1 to 1 function. Now let's show that on a graph. So let's just say we know this is an upward facing parabola. So I'm just going to put one on there. May not be in the right place, but it's enough to illustrate the fact that if you try to pass a horizontal line through it, you're going to intersect it in two places in some parts of the graph. So this one fails on the graphical method too of checking whether or not it passes the horizontal line test. So number 3, not a function. Not one-to-one. Okay, we won't spend too much time on number 4 because we already went through some of these. What's going on here is you can see that you've got 2 1s in the y column. So whenever you've got duplicates in either the x column or the y column, then it's not going to be a one-to-one function. So this is even if whether or not it's a function at all. So right there you can make a quick deduction that this is going to have to be a no. All right, this one here is not one-to-one because it's got duplicate values in the y column. So next, let's actually find some of these f inverses. So the steps are that you replace f of x with y, you switch places with the x and the y, and then you solve that new equation for y, and then once you've got it solved for y, you replace y with this symbol f inverse of x. So here's an example. So first step, y in place of f of x. So we've got y is equal to the square root of 3x plus 14. Second step, switch x and y. Third step, we solve for y. So in this case, the y is under the radical, so we're going to have to get the radical off by squaring both sides. So we'll get x squared is equal to 3y plus 14. Then I solve for y. So if I move the 14 over to the other side, I'll have 3y is equal to x squared minus 14. And then I divide by 3. So my inverse function is going to be x squared minus 14 over 3. And then the last step would be, instead of saying y, I'm going to call f inverse of x is equal to x squared minus 14 over 3. So this is my unique inverse function of the original function f of x. So we'll try another example here. So first step, y is equal to 4 plus cubed root of x. Second step, switch x and y. Third step, solve for y. So I want to isolate the y term. So I'm going to say the cube root of y is equal to x minus 4. Now we want to cube both sides to undo the radical. So that gives you y is equal to x minus 4 cubed. Change y to f inverse of x. And there you have it. So here's another one. We're going to find the inverse of this rational function. First step, f of x is y, 3x minus 5, 4x plus 6. Switch x and y. All right, so now we've got a y in the numerator and a y in the denominator. So let's get this all into one level. So let's say 1 times 3y minus 5, which is 3y minus 5, is equal to x times 4y plus 6. So in essence, I cross multiply. So it's all on one level. So let's distribute out that x. So that's 4xy plus 6x. Now we're solving for y, so we're going to combine all of the y terms onto one side and all of the non-y terms onto the other side. So I'm going to subtract 4xy over to this side. So I get 3y minus 4xy minus 5 is equal to 6x. All right, I have this 5 here without a y in it. I'm going to move that over to the other side. So I'll have 3y minus 4xy is equal to 6x plus 5. All right, now let's factor out a y. So finally my y is starting to emerge by itself. So then if I divide by 3 minus 4x on both sides, I should finally have y by itself. And then our final step would be to call this f inverse of x instead of y. And there we have it. So that one required a few more algebra steps, but still the basic procedure. Here's another one. So we're going to say y is equal to 2/3 x minus 1. We're going to switch x and y. We're going to solve for y. All right, we need to multiply by the reciprocal to cancel that 2/3 in front. So cancel, 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 cancel. So we're going to say y is equal to distributing the 3/2 to both of those terms. And then we're going to say f inverse instead of y. F inverse of x is equal to 3/2 x plus 3/2. So I'm trying to move as quickly as possible. So remember, you're able to pause, obviously, during this set of notes to write it down at your own speed. So hopefully you're writing everything down. So what I'm doing here is I'm trying to cover a little bit of everything so that we have everything covered that you could potentially see in your homework set. So here's one with the 7th power. So this is y is equal to 3x to the 7th minus 8th. So I'm going to switch x and y. I'm going to solve for y. Isolate your y term. Divide by 3. All right, now I need to get it to say y, so I need to take the 7th root of this here. All right, and that gives me y is the 7th root of x plus 8 divided by 3. So that 3 is underneath the root. So you got to make your root long enough here so that you've got that whole thing underneath it. All right, and that you're not just covering only the top part here. So all of this under the root. And then the last step would be to say f inverse of x is equal to the 7th root of x plus 8 divided by 3. This is our last problem, and one of the more interesting ones. It says, given the function f of x is the quantity x minus 5 squared, restrict the domain so that it is a one-to-one function and find the inverse of the function within this domain. So the implication is that this must not be a one-to-one function like it is, and that we need to do something about restricting the domain. Let's see why that's the case. So if I look at a graph of x minus 5 squared, that's a right translation of 5 of the parent function y is equal to x squared. So it's a quadratic facing upward 5 places to the right of the origin. All right, so there it is. Now you can see that if you try to pass a horizontal line through it, you're going to hit in more than one place, and it's going to fail the horizontal line test. So it won't be one-to-one function, and therefore it won't be invertible. All right, so what we have to do now is get rid of some of this graph, restrict the domain so that it does pass the horizontal line test. Now, depending on your problem, you may be asked to pick one piece of it or another piece of it, but I'm just going to say somewhat arbitrarily for this problem here that I'm going to cut off this piece of the graph here, and I'm only going to talk about the decreasing section of this graph. So let's write the domain and range of this piece of the graph here. So the domain is anywhere between negative infinity and 5, and the range is anywhere between 0 and positive infinity. All right, so these are all possible x values, and these are all possible y values for the function f of x. Now, after I invert the function and I get f inverse of x, what's going to happen is that your domain and range, of course, are going to switch places. So your range will now be negative infinity to 5, and your domain will be 0 to infinity. All right, so these will be my x's for my f inverse of x, and these will be my y's for f inverse of x. All right, so now we're ready to go ahead and find f inverse of x using our procedure. So instead of f of x, we say y is equal to x minus 5 squared. Switch x and y. So that's basically what we're doing. We're switching the domain and range. Now we're going to solve for y. So we're going to take the square root of both sides. So we'll have plus or minus square root of x, since it's an even root, is equal to y minus 5. Now I'll have y is equal to 5 plus or minus the square root of x. All right, now here's where the domain and range come into play because of that plus or minus here. All right, it may be one or the other and not both. All right, so if I look at my my possible x values, it says they go between 0 and infinity. Now we're in the all real numbers range, of course. 0 is okay, square root of 0 is 0. Any positive number is okay. So this will be okay for x inputs in this range 0 to infinity. All right, now the output, the y, has to be no greater than 5, but it can be less than 5. All right, so let's test each one of those out there, the plus and minus. So if I do the plus, 5 plus square root of x. Square root of x is a positive number, so you will see that you'll get bigger than 5 every time you add a positive number to it. And then you'll go past this 5 here, and that won't work for our domain and range that we've got here and here. Okay, so we can't have plus here. So now, let's try minus. So we have the minus there. You're at most 5, because if you subtract a number from 5, you're going to keep going down and down and down, but you're never going to go over 5. So we're going to restrict this to the minus and not the plus. Okay, so if you're not careful when you're doing these, you could very well make a big mistake up at this point here and only say that you've got the plus version here, and then you'll get the sign wrong here. All right, so now we can conclude that f inverse of x is equal to 5 minus the square root of x. So make sure you took good notes on this problem, because it might show up on a quiz again. You never know. So as usual, if you have any questions about anything that you encounter in the homework set, just let me know via Remind or email.